Hey guys, we have a question here about projectile motion. We're given the initial velocity and the angle of elevation here. We're also told to use 10 meters per second squared for gravity, and we have three parts to this question. One is A is the range, B the maximum height, and C is the speed. So let's get started. The first thing we need to do is calculate or find our position vector. To get our position vector, we have to understand that we're given the velocity of the projectile, the initial velocity, but we need it in its components. So the y component and the x component. So this is our y and this is our x components. So to get our x component of velocity, or the initial x component of velocity, we're gonna have to do our formula, so v naught cosine of theta, and similarly for the y, it's going to be v naught but sine theta because this is in the y direction. Okay, so according to the question, we are given that our initial velocity is 160 and our angle is pi over 3 radians. So let's plug that in. So we're going to have 160 times the cosine of pi over 3 radians. Now, if you're using your calculator, make sure that you're in the radians mode and not the degrees mode. So we're going to be doing the same thing for our y, or our y component for velocity, and that's 160 times sine of pi over 3. And for v naught x, I'm going to get 80, and then for my y, I'm going to get 80 times root 3 meters per second. Okay, now using Newton's second law, I know that in a projectile's path, acceleration is always pointed downwards and has the same magnitude. Even at the very top or the very bottom, acceleration is always going to be -10, and that's in the y direction. There's never any horizontal component, so we know that A equals 0, -g. So our initial conditions for our projectile for velocity are v naught x and v naught y, and that's going to be important because to get our velocity vector, we need to integrate acceleration. Now, this is 0. So when we integrate that, we're going to just get our initial condition, which is v naught x. So v of t equals v naught x, which is over here, but I'm just going to write v naught x over here for now. And then for the y value, we're going to have to integrate -g with respect to time. And we will end up getting v naught y minus gt. So we're including our initial conditions in this case. Now that we're here, we can plug in our values. So we know that v naught x equals 80, and then we also know that v naught y equals 80 times root 3, and our g value is 10 from the question. So let's go ahead and plug what we have so far. So v of t equals 80, 80 root 3 minus 10t. To get position, we're going to have to integrate this. When we integrate, we're going to get that our position function is the integral of velocity. So that's going to be 80t, 80 times root 3 times t minus 5t squared. So this is our position function. Now let's go on to part A of this question, which is finding the range of the projectile. The range is when we have maximum position in the x direction. So where is the object landing? This is also when y equals 0. This is the second time, so it's going to start at y equals 0, and it's also going to end at y equals 0. So based on that, I'm going to set this part of my position vector to 0. So it's going to be 80 root 3 times t minus 5t squared equals 0. So when I set this in my calculator, when I solve for t in my calculator, I'm going to get t equals two solutions because we have a squared. It's going to equal 0, but it's also going to equal 16 root 3. Because we're looking for the range, we don't want the time that it starts to launch or it just launched. We want the time when it lands. So we can disregard the 0 and just focus on 16 root 3. Okay, now we can use our x part component in our position function to find the distance. So 80 times 16 root 3. So I'm just plugging in this time into our x to get the position for x. So when I plug this into my calculator, I'm going to get 1,280 times root 3 meters, which is also approximately 2,218.2 meters. So that's our answer for part A. Now, moving on to part B, which is maximum height. To find maximum height, this is exactly when the velocity is 0, the vertical velocity is 0. So at this point, there's only horizontal velocity. So horizontal velocity is constant throughout the projectile's motion, whereas vertical velocity, so it's shrinking, and there's none over here, and then we're small and we get bigger as we go. So this is vertical velocity. So at the very top, we notice that vertical velocity is 0. So what we can do is use our velocity function. So over here, we're going to use this function over here and more of this in particular. And we're going to solve for t. So 80 root 3 minus 10t equals 0. And in this case, time equals 8 root 3 seconds. Okay, now to find the y max, I can plug this time into my position part component for the y. So that is 80, it's going to be 80 root 3, just go back up to check. Okay, so times t, so that's times 8 root 3 minus 5 times t squared. So that's going to be 8 root 3 squared. And when I solve this in my calculator, plug these numbers in my calculator, I get that this equals 960 meters. Moving on to our last part, part C, which is the speed at impact. We already know that the object lands at its maximum distance at a time of 16 root 3. And to calculate the magnitude, we can just plug this time into our velocity function, which is right over here, our velocity function, and then find the magnitude of that. So let's go ahead and do that right now. So for part B, we know the time equals 16 root 3 from this part A over here. Sorry, let me label this part C. Perfect. 16 root 3. And I know that my velocity vector is 80, 80 root 3 minus 10t. Perfect. So 10t. So when I plug in 16 root 3. For t, I'm going to get that 80, 80 root 3 minus 10 times 16 root 3 equals 80, 80, negative 80 root 3. Okay, perfect. So now we can move on and find the magnitude of this vector. So the magnitude of the velocity is going to be the square root of 80 squared plus negative 80 root 3 squared. And when I solve for this, I'm going to get 160 meters per second. And that is my answer for part C. So let me highlight this and let's review our answers. So for part A, the range, we have a range of 2,218.2 meters. For part B, we have a maximum height of 960 meters. And for part C, our speed at impact is 160 meters per second. Don't forget your units.